Okay, so we have times that we're going to see something that's an angle and it's not just a theta or it's not just an x. And
7-3 homework.
we what?
That was in the 7-3 homework, where it was like 2 theta.
Well, in 7.3, we had the sum and difference properties. So it was like the sine of maybe, yeah, and then we could write it, figure out a way to rewrite it so that we could do something with it. Here you go, Kobe. Here's your quiz. This one, before we start, I want to show you why we need this. So let's say we're trying to figure out if the cosine of 2 times some angle, would that be the same as just saying 2 times cosine of the angle? Okay? That's basically the question we're trying to answer. So here's how we're going to test it out. Let's pick a value for A that we could use and see what happens. And since I want to use special right triangle angles, let's say A is 30. So if I were to put in 30 degrees, here's what I'm asking. Would the cosine of 2 times 30 be equal to 2 times the cosine of 30? Now, if I look at that 30, 60, 90 triangle, this is my 30, that means the 1 is across from the 30, square root of 3 is here, and the 2 is here, okay? So if I multiply 2 times 30, that turns it into what angle? 2 times 30 is, so what I'm going to see is, will the cosine of 60 degrees be equal to 2 times the cosine of 30? If it is, that's going to be an easy way to solve this. But looking at my triangle, that would mean my 60-degree angle is actually this one up here, okay? So what would be the cosine of 60? Right, because it's adjacent over hypotenuse, so the cosine of 60 is 1 over 2. I want to know, is that equal to 2 times the cosine of 30? Well, what's the cosine of 30? Looking at my triangle. It's the square root of 3 over 2. Are those the same? Is 1/2 going to be the same thing as the square root of 3? They are not equal. So I can't just take the 2 that's in front of the angle measure and say, oh, that means I multiply 2 times the cosine of angle A. That's not equivalent. So we need some replacements that would be equivalent. And here's where we're going to write them down. You will notice cosine has multiple replacements. And it depends on what we're trying to do in our problem, which one we're going to pick. Like, for instance, some of them are going to involve both cosine and sine. So that might be an option. If we see that when we replace it, we still are okay using both cosine and sine. But some of them involve only sines and some involve only cosines. So write these down because we're going to get familiar with them. The first replacement is cosine of 2a is equivalent to cosine squared of angle A minus sine squared of angle A. Now I have a question. We've had a Pythagorean identity that involved cosine squared and sine squared. Is this that Pythagorean identity? No, because what was the Pythagorean identity? Cosine squared plus sine squared is equal to 1. Cosine squared minus sine squared does not fit that pattern for the Pythagorean identity because the sign on the cosine matches, but the sign on sine does not. So there's no way to rearrange this and replace it with something that's equivalent to 1. Cosine of 2a is going to be the difference of cosine squared and sine squared. Here's another replacement. Cosine of 2a is equal to 1 minus 2 times sine squared of angle A. So 1 minus 2 times the sine squared of angle A. And my cosine of 2A could also be replaced with 2 times cosine squared of angle A minus 1. Now, this is the point in the course where you're going to have to come to grips with the fact that I don't think we're going to be able to proficiently memorize all of these identities and be able to use them at the drop of a hat. That's why I gave you that formula sheet, because these, you want to make sure when you replace them, you're replacing them with the correct thing, all right? So if you were looking at that formula sheet that I gave you, let's pull it out real quickly and I'll show you.
Are these on there?
These are on there. Okay. So now that we saw where they were on that sheet, let's go ahead and write our replacement for the sine of 2A. It's the easy one. This one you probably will be able to remember. It's 2 times sine of angle A times the cosine of angle A. And the tangent of 2A is the only one that ends up being a quotient. It's 2 times the tangent of angle A divided by 1 minus tangent squared of angle A. All right? So those are our replacements if we have a double angle. Now, here's how we're going to use them. Suppose they tell us that the sine of angle theta is the ratio 8/17. And we know that the cosine of theta is less than 0, so it's negative. We're supposed to find what these double angles would be: sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. Now, how do you think we're going to go about doing this? The only thing they've told me is what the sine of angle theta is. I'm trying to find the sine of 2 theta, cosine of 2 theta, and the tangent of 2 theta. Well, I have a question. Why do you think they told us this part right here, that the cosine of theta is negative? What's that going to allow me to figure out? Which quadrant I am in? Very good. I can look at the sine ratio, and the sine is positive, but this tells me that the cosine is negative. Which quadrant am I in? First, second, third, or fourth? Where would the sine be positive but the cosine negative? Second quadrant. Very good. So I'm going to sketch a right triangle in the second quadrant, and that's where my angle theta is. Okay? What ratio did they give me for angle theta? Sine. And the sine is 8/17. And I know the ratio for sine is opposite over hypotenuse. What am I going to do to find the adjacent side? Exactly. I'm going to use Pythagorean Theorem. A squared plus b squared equals c squared. And if you happen to notice, this is a Pythagorean triple. If you don't know those Pythagorean triples, hopefully you're going to get more familiar with them the more often you work through these. Has anybody figured out what that missing side length is? 15. And because we're in quadrant 2, it's a negative 15, isn't it? Okay. Now that I have my side lengths for the triangle drawn, I can go back and use these double angle formulas to figure out what the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta is. So, what was my replacement for the sine of 2 theta?
2 sine theta cosine.
There you go. 2 sine theta cosine theta. So if I'm looking at my triangle, that means it's 2 times my sine is the one they gave me. That was 8/17. Looking at my triangle, what's my cosine ratio? Negative 15/17? Agreed? Okay. All I'd have to do is multiply all these parts together. It's not a pretty number, but it's solvable. I can find what it is. I think my numerator is going to be a negative 240 over, if I multiply 17 times 17, double check me, I think that's 289. It is, okay. So that's what the sine of 2 times angle theta is. Are we okay? Let's do the cosine of 2 theta. Now, this is the one where we have all the options on which replacement we would want to use. Let me scroll back up so we can look at them again. I can either do cosine squared of theta minus sine squared theta. I can do 1 minus 2 times sine squared theta, or 2 cosine squared theta minus 1. Really doesn't matter which one I pick because I've got a triangle, so I can get ratios for either sine or cosine. Do you have a preference? You want to see what happens if we do cosine squared minus sine squared? Why not? Okay. So if I were to do cosine squared of theta minus sine squared theta, my cosine was a negative 15 over 17, so we'll square that, minus sine was 8 over 17, and we're going to square that. Okay, put that in your calculator and let's see what you come up with. What did you get when you did this subtraction?
161.
Excellent. It turned out to be a positive value, didn't it? A positive 161 over 289. And now let's see what happens if we take the tangent of 2 times angle theta. We only have one formula to use, so we don't have an option here. It's going to be 2 times the tangent of theta divided by 1 minus tangent squared of theta. So if I'm looking at my triangle, 2 times, what's my ratio for tangent? Good. 8 over a negative 15. And I can think of that as 2 over 1, over 1 minus, and then I'll have to take that 8 over negative 15 and square it. All right, simplify that. Let's see what you get. Negative what?
240 over 161.
Negative 240 over 161. Did everybody get that? So let's look at the next example. It says find the values of the 6 trig functions of theta if you're told what the cosine of 2 theta is and what quadrant theta is in. Now, this one is a little bit backwards because I know what the ratio of 2 theta is, but I know which quadrant theta is in. How am I going to figure out what all the side lengths are going to be on this right triangle? Because here's what I know. This is in which quadrant? Third. 180 to 270 is a third quadrant right triangle. But I better not label the side lengths on this triangle with the negative 12 and the 13. And the reason is that's not what the cosine of theta is. That's what the cosine of 2 theta is. I'm going to have to use one of these double angle identities to get a replacement so I can figure out what the cosine of theta is. And then I can go label the rest of my triangle. So tell me, from looking at our options, what do you think would be the right one to choose for the cosine of 2 theta? Because I've got 3 options. Do I want to use the one that has both cosine and sine? Do I want to use the one that only has sine? I need to use the one that only has what? Cosine, because that's what I'm trying to find is the cosine of theta. So the one that involves cosine is 2 cosine squared theta minus 1, right? What was the replacement for the cosine of 2 theta? Negative 12 over 13. Now, that's equal to 2 times cosine squared theta minus 1. So what am I going to do to solve for cosine of theta? What like terms do we need to get together in the next step? Remember, I'm trying to get this cosine theta by itself. I need to get rid of this minus 1. So if I add 1 to both sides, here's where it's helpful if you stop and think, all right, I need a common denominator if I'm adding fractions. How could I write 1 so it's got a denominator of 13? That's right, 13 over 13. And that would mean 13 over 13 plus a negative 12 over 13 would become 1 over 13, right? Is equal to 2 times cosine squared of theta. Now, I'm going to have to do what? Right, I can divide by 2, or I can think of it as multiplying times 1/2. Multiplying by the reciprocal. That causes the 2's to cancel. And I know the cosine squared of theta is going to be the fraction 1 over 26. We're really close. How do we find cosine of theta now? Take the square root of both sides. So the cosine of angle theta is going to be the square root of 1 over 26, which I could write as 1 over the square root of 26. Now, remember, when I'm taking the square root, there's both a positive root and a negative root. Since they've told me that angle theta is in the third quadrant, should this be a positive or a negative value for cosine? Is cosine positive or negative in the third quadrant? Negative. Okay, did that make sense? That's what we're going to have to figure out. Now we can go to the third quadrant triangle that we drew for angle theta, and if we know the cosine of theta is negative 1 over the square root of 26, that would mean this side length is negative 1, and my hypotenuse is the square root of 26. You're going to find, in a case like this, don't rationalize here because I actually need to know what those side lengths would be before it was rationalized. Now, how am I going to find the missing side length for the opposite side? What did we do a minute ago when we needed it? Pythagorean Theorem. This actually ends up not being too bad because if my hypotenuse is the square root of 26, when I go to plug into a squared plus b squared equals c squared, what happens if you square the square root of 26? It's just going to turn into 26. And if I square the negative 1, that just turns into 1.
26 minus 1 is 25, and then square root, that's 5.
Exactly. A is going to equal 5 because it was the square root. Does that make sense? This becomes 26. This is 1. And if a squared is equal to 25, then a is going to be 5. Now, remember, there's both a positive root and a negative root. If I'm in the third quadrant, what sign should this part of the triangle be? It's going to be a negative. Now that the triangle is labeled, would it be hard to go through and identify what the sine of theta is, what the tangent of theta is, and all the other ratios? Not at all. I'm just to save a little time, I'm not going to write all of them out. We already knew from solving over here that the cosine of angle theta, and at this point you might want to rationalize, would be a negative square root of 26 over 26. What would my sine be looking at this? I could first write it as negative 5 over the square root of 26, couldn't I? And then if I want to rationalize it, I can. And it's not going to be a big deal to write out the other remaining ratios. The trick is being able to see how to find that first ratio so you can then go label your triangle. All right, so give me a little signal. Are we good, working on it, or really kind of nervous about this? All right, so good deal. Now, here's another way that you can use these double angle identities. Look at this thing for a minute on A. Is there something about that that looks familiar? I've got 2 cosine squared of 5x. Does that look like one of those identities for cosine of 2a? Yeah, since the cosine of 2a is equal to 2 times cosine squared of a minus 1, looking at this, wouldn't it have to be true that a is equal to 5x? So now that would mean that if a is 5x, wouldn't this be the same thing as the cosine of 10x? That would be a more concise way to write what that's equivalent to. We're not solving it, we're just rewriting it using one of those double angle identities. This one is kind of close to something else as well. What do you notice that it's very similar to? For, well, the identity for which one? Is it a cosine or a sine or a tangent? It's the sine. If you remember, the sine of 2a was equal to 2 times the sine of a times the cosine of a. Okay, now, what we have is similar, but what's missing? There is not a 2 in front of the sine 165, cosine 165.
Well, there is now because you just added one.
Well, here's what we would have to do, though. Since we have the sine of 165, cosine 165, okay, wouldn't that mean if I'm going to insert a, since the 2 is not there, if I insert the 2, wouldn't I then need to come back and divide both sides by 2? Wouldn't that be legal? Since the original here did not have the 2, I can put the 2 there as long as I also divide by 2. Because what happens if I have 2 on top, 2 on bottom? Is that going to be equivalent to what we have over here? But if I'm going to take this identity and divide this side by 2, I also have to do what? Divide the other side by 2. Does that make sense? Okay, so I'm just applying rules of algebra here and manipulating it so I could get this side to look like what I have. And now it does. Here's what we have to decide. What is A? From looking at this. If this was my formula, A was what value? 165. So now if I want to find out what I'm going to get over here, that would mean I'm going to have sine times 2 times 165 for my angle, but then that's going to have to be divided by 2. So if I can find the sine of 330 and then take that value divided by 2, I'll know what it is. Now here's a question. Sine of 330, would that be one of my special right triangles?
I'm sure it would.
It would. You are so right. Which quadrant? 330's got to be in quadrant 4. And if this is 330, wouldn't that make this a 30-degree angle inside my triangle? Absolutely. So this has a side length of -1. This side is square root of 3. This side is 2. And now if I ask you what's the value for sine of 330, you're going to tell me what? I'm going to have a negative 1/2, and divided by 2 is the same thing as multiplying times 1/2, which means this is equal to what? Negative 1/4. That one we were actually able to solve completely. Here we were just replacing it with an x without being given any information about what angle x is. We couldn't do anything else with it. Okay? Now this one, we're going to modify it a little bit. We do have an identity we're going to derive. But instead of writing it in terms of the sine of x, I want us to write it in terms of the cosine of x. Okay, going with the sine of x is a little too complicated in my opinion. We have a double angle identity. So if it had just been cosine 2x, I'd have no trouble doing this. But this says the cosine of 3x. So think with me. How could we rewrite the cosine of 3x? We could turn it into what? Think back to 7.3. Could I write this as a sum?
Yes.
So 3x would be the same thing as what?
2x plus 1x.
Yeah, I could write it as the cosine of 2x plus x, because 2x plus x is 3x. So we're going to kind of take some things we did in 7.3 and combine them with what we're now learning in 7.4. Okay, if this is now written as a sum, that means I can apply that cosine of a plus b property. Do you remember what that is? If you don't, look it up on your formula sheet. So how do we rewrite the cosine of a plus b? It's
Cosine A, cosine B, minus sine A, sine B.
excellent. Cosine a, cosine b minus sine a, sine b. So this becomes cosine of 2x times the cosine of x minus the sine of 2x times the sine of x. Okay. Now, what can we replace out of what we just wrote? Do you see double angles? I got a cosine 2x and I've got a sine 2x. Now, here's how I would kind of think my way through this. I have multiple options for how to replace cosine 2x. Agreed? But how many options do I have for replacing the sine of 2x? Only one. So let's do this. Let's go ahead and replace the sine of 2x with what? Minus 2 times,
2 sine cosine.
that's right, sine of x, cosine of x, and then I have this other sine of x that was already here that's going to be multiplied together. Now here's what I'm noticing is when I clean this up, I'm going to end up with a sine squared, right? So what do you think might be a good option to replace my cosine 2x with?
Sine squared.
How about the one that uses sine squared? So let's do that. Let's rewrite the cosine of 2x as 1 minus 2 sine squared of angle x times the cosine of x. And let's see what happens. Because here, I've got to use distributive property, don't I? So that's going to turn into, tell me what to write. Cosine of x, because I'm distributing cosine of x through this first parentheses, minus what? 2 sine squared of x, cosine of x, right? Minus 2 sine squared of x, cosine of x. Oh my. Well, they didn't cancel out, but I can do what with them? I could add them together. They're like terms. These are identical. And so if I have a negative 2 of these sine squared x cosine x things, and I have another negative 2 of them, that means I now have cosine of x minus 4 sine squared of x cosine of x. All right, we haven't quite gotten there because we're supposed to be writing this in terms of cosine, and I still see that I've got this sine squared of x thing in there. So what can we do? Think back even before 7.3. Do I have some sort of replacement for sine squared of x I could use that uses cosine? Think Pythagorean. Oh, come on. Sine squared of x is equal to what using my Pythagorean identities? You got it. If I replace sine squared of x with 1 minus cosine squared of x, now I'm going to have only cosines, cosine of x's. And that would mean I've still got a little bit more distributive property to use here. So this cosine of x, and that's going to be, in fact, you might want to think about putting this cosine of x with this minus 4, and that's what we're distributing through. So a negative 4 cosine of x times 1 is a minus 4 cosine of x, and a negative 4 cosine of x times a negative cosine squared of x turns into a what? Negative 4 times the negative becomes a positive 4, and the cosine squared of x times another cosine is cosine to what power? If I've got cosine squared times another cosine, that's cosine of x to the 3rd power. I have some like terms right here. Last step, I'm going to get a negative 3 of these cosine of x terms plus 4 of cosine cubed of angle x. Now, everything is in terms of cosine of x. All right. I don't want you to stress over it. This is not something you would be likely to have on the test, all right? But it does give us a chance to work together to see if we can recognize the replacements. That's the critical part of this. You want to be able to realize, well, if I rewrite it where it looks this other way, that might let me replace it with something else to eventually get it to a form you can do something with it. That's what we're trying to do with this, because sometimes you do have to do that in calculus. All right, questions so far? Everybody's still hanging in there, right? Okay. This one, just to save a little time, we're not actually going to do it, but what I've tried to do is in the notes give you some of these application problems on where people would be using this. And we talked last time about the alternating current versus direct current, and the fact that when you're working with electricity, if you happen to go into electrical engineering, man, you're going to be doing a lot of stuff with this. And so this talks about how you can calculate the maximum wattage of something, all right? In other words, you want to make sure if you're creating a product that it's not going to require more watts than you would have available out of your outlet, right? Okay, so this would tell you how you could figure that out. We're not going to go through the process, but it's very simple as far as plugging in, and you would end up with an easy way to see what, as long as you know the formula you need to plug into. Now, we have some other identities that we're going to need to use. They're also on that sheet. These are product to sum and sum to product identities. In other words, if we have two ratios being multiplied together, notice we're only looking at sines and cosines. This would give us an alternate way that we could rewrite this. Now, let me ask you something. That cosine A times cosine B, that looks like part of what? Remember when we did the sum and the difference with cosine? Because we ended up with the cosine A, cosine B, and then it would either be a plus or it would be a minus, and then you'd have your sine A, sine B. This is kind of a variation of that. Look at what this is equal to. It's 1/2 times, and in the bracket, we're going to have the cosine of the difference, A minus B, plus the cosine of the sum of A plus B. So there's a little bit of a connection there. It's kind of, that way we're not just totally recreating the wheel.
What is that? Right in the bracket?
Okay, yeah, I'm sorry. Like I say, writing with a stylus is kind of hard for me.
Cosine.
So that's a cosine, A minus B, plus cosine of A plus B. Okay, so it only uses cosines, but we're going to have the sum of the difference of the cosines and the sum of the cosines inside that bracket, and then we multiply it times 1/2. What about the sine A, sine B? Is that the other part of that sum and difference formula for cosines? Yes, so guess what this looks like? It's going to be 1/2 times. Now what we're going to do is we're going to start with the cosine of A plus B, and then we're going to subtract out, oh, I'm sorry, I wrote that in the wrong order. We're going to start with the cosine of A minus B, let's fix that, minus the cosine of A plus B. So it looks just like the one we did above, except instead of adding these two parts together, you subtract. Okay? Not that I expect you to have these memorized. You will use your formula sheet, and you can find them on there, but you can see the similarity. Now, when we talked about the sine of A times the cosine of B, that was part of which one of those identities? When we had, instead of cosine of A plus B, it was the sine of A plus B. So sine A cosine B becomes 1/2 times the sine of angle A plus B plus the sine of angle A minus B. These are the ones where we reverse the order and we put the A plus B first. And that means the cosine of A times the sine of B is equal to 1/2 the sine of A plus B, and what do you figure comes next? Minus the sine of A minus B. Lots of formulas here. So let's see if we can figure out how to use this in this next example. We're supposed to write 6 times the sine of 40 degrees times the sine of 15 degrees as the sum or difference of two functions. So it doesn't tell us we have to solve it, does it? It just tells us to write it as the sum or difference of two functions. So tell me, if I have 6 sine 40 sine 15, that would mean that this 40 would be which part, an A or a B? I think that would be an A, and 15 would be a B, and that means I've got a sine A, sine B pattern here. Now don't forget we've got a 6 in front, so we'll want to keep that, but how am I going to rewrite this part? So if I've got sine A, sine B, and I look up here, I need to use this, don't I? So tell me what to write down.
Cosine A plus B.
Before I do that, I better write what? 1/2. And then I'll have cosine of, is it A plus B or A minus B?
Minus.
A minus B. So 40 minus 15. And then I have a subtraction sign. And then I'm going to have the cosine of A plus B. So I write 40 plus 15, right? So if we were to clean this up, what's my new coefficient now?
3.
3, because I've got to multiply the 6 times the 1/2, so that gives me 3. Cosine, now what angle am I going to put in the parentheses? 40 minus 15 is 25? Minus the cosine of, what's this going to be? 40 plus 15 is 55. Now, those are not special right triangle angle measures, are they? So, unless somebody had already told me how much the cosine of 25 is or the cosine of 55 is, this hasn't helped me necessarily. I mean, I could just do 6 times the sine of 40 times the sine of 15 if I'm going to be plugging in the calculator. But the point is, sometimes you can rewrite these and end up with special right triangles, or you might find you didn't know what the 40 and the 15 were, and they were asking for exact values, but they gave you the exact values for the 25 and 55. So this would have given you a way to get there and find the answer. Okay, look at, well, actually, we're going to now rewrite these going the other direction. If they are sums or differences, then we have sum to product identities that we can use. And again, these are on your notes or on your formula sheet. So sine of A plus sine of B is equivalent to 2 times the sine of, we're going to add A plus B but divide by 2. We're going to take half of whatever A plus B is times the cosine of half of A minus B. And again, you can see some parallels if you think about this, how this ties in with those others that we had. When it's the difference, sine A minus sine B, that's the same as 2 times the cosine of A plus B over 2 times the sine of A minus B over 2. So the calculation for the angles are the same in these, but we're switching the order of the sine and the cosine that go with them. When it's a cosine of angle A plus cosine of angle B, we have 2 times the cosine of the sum, A plus B over 2, times the cosine again of the difference divided by 2, A minus B over 2. Lots of formulas here. And the cosine of A minus the cosine of B, this is the only one that is negative. It has a negative 2 times the sine of A plus B over 2 times the sine of A minus B over 2. There's just practically no way to have all these memorized and ready to use when you test. You're going to need to reference these. So let's try this example. We're going to write the cosine of 3 theta plus the cosine of 7 theta as a product of 2 functions. So if I'm looking at these formulas up here, it looks like I need this one. Wouldn't you agree? Third one down. Cosine of A plus cosine of B is what this looks like. That would mean A is what? 3 theta. B is 7 theta. Okay, so my formula, I'm going to write it out first. Cosine of A plus cosine of B is this. 2 times the cosine, A plus B over 2, times the cosine of A minus B over 2. So if I'm replacing this using 30 for A, 70 for B, that's going to be 2 times the cosine of, if A is 30 and B is 70, that's going to be 100 divided by 2, right?
Is it 3 theta or 30?
Oh, 3 theta. Oh, thank you. Yes, that's a theta. So we're going to have 3 theta plus 7 theta, which is 10 theta. And 10 theta divided by 2 is 5 theta. Does that make sense? Okay. And then when we go to the cosine of A minus B, if A is 3 theta and B is 7 theta, what do I get when I subtract those? A negative 4 theta divided by 2 turns into?
-2 theta.
And you're done. That's all you have to do. Okay? Well, I say that's all you have to do. There's actually one little housekeeping thing we should do. Do we want to leave that negative 2 theta as our angle measure? Because we really ought to write it with a positive angle measure. That means we need to figure out, is cosine even or odd? Do you remember? Even. And when it's even, that means we could replace the cosine of negative 2 theta with what? It's the same thing as the cosine of positive 2 theta. When it's even, that negative angle measure is going to be equivalent to whatever the positive angle measure is. So we would replace that with that for our final answer. We have even more identities. Aren't you excited? Okay. These are the half angle identities. In other words, if we have the cosine of, and maybe it's some angle measure divided by 2, we're going to see there's both positive and negative symbols that will be in front of these on our sheet, and that's going to tell us that we have to be careful we choose the right sign based on the function under consideration and what quadrant we are in. Okay, so kind of like when we started this lesson, we had to look at the information we were given to figure out the quadrant, and that let us decide what the SIGNS would be for each of the values we were looking for. Now, if we're looking for replacements for cosine, we only have one, and it is either a positive or negative, and the replacement is the square root of, and it's a fraction, 1 plus the cosine of angle A divided by 2, all of it under the radical. So plus or minus the square root of 1 plus cosine A divided by 2. There is only one replacement for the sine of A divided by 2 for the half angle, and that's this. It's either positive or negative, and we have the square root of 1 minus the cosine of angle A divided by 2. Okay, so they're very, very similar. The only difference is one is 1 plus cosine of A under the radical in the numerator. The other one's 1 minus cosine of A. But look, we have 3 replacements for tangent on this one. So where we had all the options for the cosine on the double angle, when it's a half angle, it's the tangent that has the variation of replacements. So positive and negative on all these. The first one is the square root of 1 minus cosine of A over 1 plus the cosine of A. All right, so there's only cosines in that replacement, but they're under a radical. We could also replace tangent of A over 2 with something that does not have a radical. Sine of angle A over 1 plus the cosine of angle A. Now notice, because there's not a radical, we don't need the plus or minus sign. All right, it'll take care of itself. It's with the radical, when I take the square root, I know I've got both a positive and a negative root, and that's where I'll have to pay attention to what quadrant I need to be in to get the right sign. And the last replacement is 1 minus the cosine of angle A, and that's divided by the sine of angle A. All right, so let's see if we can use these half angle identities to find the exact value of the sine of 22.5 degrees. Now, if I want the exact value of the sine of 22.5 degrees, and I go to my calculator, I can't get the exact value, I'm going to get a decimal approximation. But using this half angle identity, okay, that would mean if I'm using the half angle identity for cosine, then the cosine of, well, actually, we want to end up with cosine in the answer. And that's because if you look at the replacement for sine, it has cosine in it, okay? So the sine of 22.5 degrees, wouldn't that be the same thing as the sine of 45 divided by 2? Isn't 22.5 half of 45? So what that tells me is my A is 45. So if I go back and I look at what the replacement is, now I'm going to end up with this replacement, positive or negative, square root of 1 minus the cosine of, what did we decide A was? 45. And then that's going to get divided by 2. All right.
Sine of 45 is square root 2 over 2.
Very good. If I sketch out a 45-degree angle, that's a 1 square root of 2. So the square root of 45 is 1 over the square root of 2, or well, let's just go ahead and write it as 1 over square root of 2 for right now, okay, over 2. How about, you want to go ahead and rationalize the 1 over square root of 2? I think we should. So if we multiply that by the square root of 2 over the square root of 2, we're going to have, let's come over here. And actually, do we need to keep this plus or minus? If it's the sine of 22.5 degrees, which quadrant are we in?
First.
And if it's first quadrant, my sign is just going to be positive. So I really don't need to write the plus or minus. We just need the positive of this. So if this is rationalized, I can think of it as 1 minus, 1 over 1 minus the square root of 2 over 2, right? In my numerator. And my common denominator would be 2, wouldn't it? So if I write that as 2 over 2, I now have the square root of 2 minus the square root of 2 over 2, and I'm dividing that by 2, which is the same as multiplying by 1/2, isn't it? Okay. You with me so far? All I did is get rid of the complex fraction part by taking the numerator, and since it's divided by 2 over 1, that's the same as multiplying it times 1 over 2. And that's going to help me a little bit, because here's what I'll end up with. The square root of, I still have the 2 minus square root of 2 in the numerator, but the denominator is now what number? And that's a perfect square. So here's how you're going to write your final answer. Your numerator is the square root of 2 minus the square root of 2. We get a square root under a square root in the numerator over what would be my denominator without a radical? Because the square root of 4 is 2. The trig is not bad here. It's the algebra that's a little bit nasty.
2 minus the square root of 2 over 4 turned into 2 minus the square root of 2 over 2?
Because if all of this is under the radical here, remember you can think of it as the square root of the top over the square root of the bottom. So our square root of the numerator is still the same, but the square root of 4 is 2. And then we can stop because the denominator doesn't have a radical in it anymore. Okay, it's been rationalized without having to actually go through the process of rationalizing it. We just cleaned it up. All right, let's see if we can find the exact value of tangent of 75 degrees if we use this replacement for the half angle property. Okay, so we want to get the tangent of 75 degrees, and to do it, we're going to use the tangent of a over 2 is equal to this. Now, that means, what would a have to be so that when it's divided by 2, I get 75? 150. Very good. That's equivalent, isn't it? So that means our a is going to be 150. Now we can use this identity, so we'll need the sine of 150 and we'll divide that by 1 plus the cosine of 150. And I think I can do something with a 150-degree angle because that means I'm in the second quadrant. And if this is 150, that makes this 30, doesn't it? All right, let's identify what these side lengths should be for this 30-degree angle.
Sine is 1/2.
Okay, and is it positive 1/2?
Yes.
Because this is a positive 1, this is a positive 2, this has got to be what value on this side? Negative square root of 3, right? Okay, so I've got all my side lengths identified, so I can easily find any ratio I need. The sine of 150, Chase just said was 1/2. He is exactly right. So we're going to have 1/2 divided by 1 plus, what's the cosine of 150? Square root of 3 over 2, and it's negative. Now, I'd like that to be a single fraction. So can I think of this 1 over 1 as being 2 over 2? And this is going to be the same thing as 1/2 divided by, and if I put this together, that would be 2 minus the square root of 3 over 2, wouldn't it? Just taking this denominator right here and writing it as a single fraction. And that would become 2 minus square root of 3 over 2. But a fraction divided by a fraction is the same thing as multiplying by the reciprocal. So let's rewrite that as 1/2 times 2 over 2 minus the square root of 3. And what can I do with the 2's? Cancel them out. All right. We've got 1 over 2 minus square root of 3. We're not supposed to leave radicals in the denominator. So how can we fix that?
Move to the top.
Well, I can't move it to the top because it's a single fraction. But I could multiply by the what? Conjugate. Remember when there's two terms and one of them is a radical? We can get rid of the radical if we multiply by the conjugate. So I would multiply by 2 plus the square root of 3, but if I multiply the denominator by that, I've also got to multiply the numerator by that. It's like multiplying by something that's equivalent to 1. So that's going to give me 2 plus the square root of 3 in the numerator over, let's see what you get in the denominator. 2 times 2 is 4. The reason that I'm using the conjugate is because the outer and the inner cancel out. I get a positive 2 square root of 3 plus a negative 2 square root of 3. So all I have to do now is multiply last times last. What is a negative square root of 3 times a positive square root of 3? And 4 minus 3 is? So 2 plus square root of 3 over 1 is just 2 plus the square root of 3.